We are live. Hello everyone and warm welcome to Func Prog Sweden. This time, for the second time this year, we are at the Kivra office in Stockholm. It's a very nice office. Thank you very much, Kivra, for letting us coming to your nice office here in Stockholm. Thank you very much. And I'll jump straight into it. First, there will be a short introduction by me, Magnus. Then we'll jump into Super Haskell, an introduction to Agda by André. And then after that, we'll do schema management with Scala Meta by Lars. Fun thing, Lars was actually supposed to do this presentation 3.5 years ago, but then Corona came. And now, 3.5 years later, he's finally here and doing the presentation. So it's really nice. It's really nice. Yes, and then in the end, I'll just sum up the meetup. Again, thank you very much, Kivra, for having us here. If you want to talk to people at Kivra, look for people in green. These, but green. Yes. Also, thank you very much, Other Beat, for sponsoring the video stream. And if you want to know more about Other Beat, go on internet. And then the coming schedule for the rest of the year. 7th of November, we're back with another meetup. And then 5th of December, we also have another meetup. And then in January, we haven't set the date yet, but of course, we'll have another meetup. Yes. If you want to support the Func Prog Sweden meetup, head over to Meetup and join the meetup community. Very simple. And of course, you should head over to YouTube and also follow, subscribe, do all the stuff you can on YouTube. Google will love you, and we also will love you. And we have also started the Discord channel. Sometimes it's hard to ask longer questions in the YouTube chat. Jump into Discord and you can ask long, tricky questions to the presenters. So, if you have questions during the presentation, just shout out in the chat or in the Discord channel. Or if you're in here, raise your hand and, oh, I have a question, please. Yes. With that, let's get started. First presentation, Super Haskell, an introduction to Agda by André. Welcome.
Thank you.
Welcome, Andrea. And I leave the laptop to you.
Thanks, Magnus.
Yeah, you're welcome.
Yeah. All right. Mic is working. Let's see here. Let's get started. All right. Thanks, everyone, for coming and for indulging my talk. Let me just do a little bit of setup on my phone here. And let's get into it. Let's explore this language that I like to call Super Haskell. So first, just a very short introduction to me. I'm a Brazilian software engineer, but I've been in Sweden for around 3 years. I'm an FP consultant at Autobeat, working in PureScript these days, actually. And I have a master's degree at Chalmers University in Gothenburg. Did my thesis in category theory and some dynamical system stuff. That was all Agda. I'm not an expert in Agda, though. I want to give that disclaimer. But hopefully I know enough about it to whet your appetite here. So this talk is going to be, I think this is a very rough estimate. That Tilda is doing a lot of heavy lifting there. But just a little bit of philosophy and motivation for Agda, the language, and its underlying theory. And then some code where I introduce the central concept of the language to you, and then we're going to run a very small but real program using it. So why, first of all? Like, why dependently typed stuff, types? Well, the way I see it is that there is a true cost to correctness. When we're writing code, when we're doing software engineering, we usually care about whether the code is correct or not. And I see this as kind of two types of work. Like there is the implementing the code, which is writing the body of the function, so to speak. But then there is thinking about the code you just wrote, ensuring it's correct, and verifying that it does what you actually want it to do. These terms are very overloaded, the ensuring correctness and implementing here in this graph. The confidence required to deem a program correct varies. It's depending on the context you're in, you're going to have different criteria. And so does the amount of work in the implementation. I mean, some people are going to find Python exceedingly easy to write code for. Others are going to think the same thing of Haskell or Agda or any other language. And we want to strike the right balance. I think I'm a little nervous. Like in this example, it's like it matters less that your social media website is slower than usual than if your nuclear plant software has an off by 1 error or something. And we have some tools at our disposal to guarantee correctness. There's tests, which is obviously not complete. You're never going to think of every possible test to verify that your program is correct. There's trust, which is, well, this thing has been around for a long time, and it's worked for a long time, so the probability that it's going to be around and continue working is really high. That's something known as the Lindy effect. Something's been around forever, it's going to stay around forever. That's not always true. I mean, a lot of people here are going to remember the log4j issue. Azon, an ancient Haskell library, had a vulnerability in it that was caught, I think, a couple of years ago. And types and theorems are also not a guarantee that they do what even they say they do. Even their degree of confidence is not guaranteed. I mean, bugs exist in compilers. I think GHC 9.4.1 had a floating point error. And inconsistencies exist in proof checkers. There was an inconsistency was found in development version of Cubicle Agda, which is an extension to Agda, and which basically means you can prove anything if you exploit that thing. So we can never really be sure. Well, you can obviously increase our confidence, and the tool we're going to be focusing on with Agda and with, what dependent types tries to bring to the table is this idea of bridging the gap between human intention and machine code, like the thing that the electrons are going to fly around in the wires in the way that you want them to. We want to reduce the amount of times that we say, well, I didn't mean that. Right? And the way I think about types in this context is like, you know, there's these kids' toys where you have to place the right shape in the right hole. That's a sort of plumbing. I think much of programming gets down to plumbing. And if you have, so the analogy here is the shape of the hole is the type of the thing you're supposed to put in there when you're calling a function, say. And the surface in which you create the hole is like the type system. So the type system allows you to express certain shapes. Now let's imagine that there is such a thing as putting a correct shape inside of a correct hole. In this case, like you want the H1 shape to go into the H1 hole, which I didn't label here, but it's like 1, 2, 3. And you want the square to go in the square and the circle to go in the circle. Well, looking at this thing, you barely have a choice, right? Maybe you could stick the circle inside of the square there, but you'd have to try pretty hard to do that. Really, you just take the shape and you put it in. That's what this is trying to communicate. Whereas in untyped languages, it's more like you have just squares for everything. Now really you don't have any choice. You have to read the labels and say, okay, this one on the right is actually the one that's supposed to go on the left hole, and this one goes here and that goes there. So it's more cognitive work. And in super typed languages, which I think Agda qualifies as, is you can have like really specific shapes of these holes. Like your type system can express almost anything. Like there really is only going to be one thing that fits in there. But if you to go with the analogy, to stay with the analogy a little bit, if you're working on a surface where you have to carve out these holes, and the surface is too brittle, maybe you'll create a little hole, maybe you'll shave off a little piece here, but then the whole thing breaks, and then now you have a little crack over there, and that's not really what you want. On the other hand, if it's too elastic, you can just you can take one of these holes and just really push something in with everything you have, and it'll come out the other side, and it'll kind of work, like putting an any in a TypeScript piece of code, say. So we want the right material. There's such a thing as a good balance between convenience and correctness, in my view. And there's two ways in which you can not have the right materials. You cannot have it from two different directions. One is sometimes the cost of typing is too high. I don't know if you saw this news. It was very recent, but a big library in TypeScript in the JavaScript ecosystem is just dropping TypeScript. I don't know much about that, but I didn't actually expect this to happen. I thought, up to this point, I thought it was generally, yeah, everyone's going to keep adding types to everything. Because the cost of convenience can be high, which is why you see dynamically typed languages in which things are easy and nice to prototype in. They just keep adding type systems to their stuff. And getting the right material is hard. This is a little snippet of code from a PureScript library I'm working on. I don't know if you can read that, but it doesn't really matter. The point is this is a wall of code, and this is expressing something that is not that complicated. And here is an answer from Connor McBride, which is a really good programmer who knows a lot about types, and is what he has to say about the Singelton's library, which is, if you've heard of that, it's basically a mock-up of dependent types in Haskell. It's adding even more type safety than Haskell already has. And the question here was, what do we gain with singletons? And well, they're just an annoying thing that we hope we never have to look at again. But I think Agda gets really close to striking this balance. And I just have one more slide here, which is introducing the language. It's a dependently typed, purely functional language developed at Chalmers. The syntax is very similar to Haskell. There's some key differences. We'll get into that. It's based on Martin Löf type theory instead of Henry Milner. Martin Löf is a Swedish logician on the left here. This is a fun fact that the name comes from Cornelius song. And that's actually the icon. It took me a while to recognize that this was a chicken. It was created by Ulf Norell, also a Swede. There's a little table on the side here, which is shows how Agda is trying to uniformize. Is that a word? Make uniform. It's trying to blur the distinction between types and values. It's just you fling things around in a pretty uniform way. Whereas in something like Haskell, each one is its own syntactic thing, and it's a different universe of expressing things that are really equivalent. But that's it for philosophy and motivation. I hope that you're eager to look at some Agda code now. That's what I was going for with these initial slides. So let's do it. We're going to go over a few modules that I have ready here. One going over the syntax of the language, just to show you can see what it's like to define a type, a function, etc. Then we're going to go into this idea of propositions as types. How many people in this room does propositions as type, does this mean anything to you? Raise your hand if it does. All right, a few people. Cool. I want to know if I'm speaking your language here. Then we're going to have a very small matrix library with some matrix operations. And then finally, we're going to actually jump into the Haskell FFI, which is Agda's version of an escape hatch. So let's go. This is the first module where I introduced the syntax. And let me just update my little my little phone helper here. So a few words on Agda mode. I think most Agda programmers use Emacs, and I've never used Emacs, but apparently it has a lot of this control C, control something else thing, and that's just like it's a command. What, you want to ask something? Yeah. Yes, I can. Thank you.
Can we lower the light level here? Light beam.
What? Oh, because it's too dark. Okay. Ooh, I actually don't even know how to change that in VS Code. Preferred light color? No. Someone suggested something. What's? Okay. Command K, Command T. Ah, okay. Whoops. All right. Nice. That looks pretty good, actually. Thanks. I guess I can increase the font on the side here also, although we're not going to see that until the end. All right. Is that better?
Yeah.
Cool. Yeah, so Agda mode. It's a bunch of commands that as you write code, they do stuff for you. These are the main ones. And I'm going to be, the very same Conor McBride has a technique where he sticks a camera on top of his keyboard so you can see which commands he's running also. And it shows up on the bottom here. If you have a keen eye, you're going to be able to see that as I run these commands. But yeah, there's loading and type checking at single module, refining a whole. This is 99% of where Agda programming and testing and REPL stuff, that's, well, the equivalent to a REPL situation. That's where it happens. So, and the output shows up all here in this little tab. So let's just get started. First of all, here are some types and their values. This looks very much like gadded syntax in Haskell. If you're familiar with that, you say data, this is the name of the type, that's the type of the type. Yes, there's no kinds in Haskell. Types just have types. They're called sets, because really types are just a collection of values. Where, well, one, this constructor has the type 3, 2, 3, etc. And this is an example of a value of 3 and another one. Agda supports Unicode, as you can see here, with this little 2. It's very, very much not shy about that. So it's a common thing. And we're going to make lots of use of Unicode. But this is 2 different values of the type 3. That's how you define a sum type. Here's the equivalent to Haskell's either. You can see, I mean, this, if you've seen Haskell before, or PureScript or some other dialect, I would say, this looks very similar. There's a type on the left, there's a type on the right, and there's 2 ways to get an either A or a B. You can either do the left injection, which takes an element of type A and returns you an element of type either A or B, or you can do it on the right. And here's a value of either. So this is, we introduced another piece of syntax here. This is an implicit parameter. So when we call this value, when we use this value, we normally don't want to have to say what the type A is. It's just it's gonna be obvious from the context, hopefully. But sometimes, actually pretty often, we do have to give this argument. So what this is saying is that value of either has a type of either natural number or any type at all. Well, because it's a left 10, that natural number. And here is the syntax for product types. So you'll notice that there's a different keyword there, record. And well, the reason is that there is a fundamental difference between product types and sum types, co-product. They're the dual of each other, and I think it's just nicer on the eye. Personally, I like having a little section where I specify what the fields of the record are, what the product type. I mean, those 2 things are the same if you didn't know. Whenever you define a record in your favorite programming language, really you're defining a product type. And Agda makes that pretty explicit. And you can give a constructor to build one of these types up. And we see this being used here. So this is a pair where it contains one value of 3 and one value of bool. The type 6, that is. And a value of 6, you just use the constructor to build it up. Here's the definition of Haskell's tuple type, the pair of two different types. Again, it takes two types as parameters. One goes on the first field, the other goes on the second one. Pretty straightforward. This is how you construct a pair, because we gave the pair constructor a name. You'll notice that you don't need constructors to be uppercased, unlike in Haskell. Yeah, so that's pretty basic. Here's an example of how to define a function. Again, similar to Haskell. There's a function that takes two natural numbers and adds them, and a function that pattern matches on one of its arguments. So you're adding one of three values to a natural number. So if your value is 1, you add 1. If it's 2, you add 2, etc. And this still looks very similar to Haskell, I hope. And let's see some more syntactic things that are pretty cool. So Agda supports mix-fix operators. So this this function is named pretty freaky, but it makes sense when you use it. Like add this first argument to that second argument, but only if something and something else. Otherwise, pick one of them. So it takes 4 arguments, which are the four underscores here, and it returns a natural number. And you can see the body here. Let bindings, they just work like in Haskell. So you do condition 1 and condition 2. It's a Boolean operator here. And if both of them, then you sum them up. Otherwise, you pick one of them. And how do you pick them? Well, you use this function defined in a where block. And this function uses the with keyword, which is Agda's version of case. And it's actually dependent pattern matching, which means that when you pattern match on a value of this, when you pattern match on an expression inside a with, the compiler knows something about the types in the pattern match body. And I'm pretty sure we'll see examples of using with. I think it's not going to be necessary for most of the stuff we use. And in this case, this is a non-dependent pattern match. It's just if it's false, then this returns M. Otherwise, it returns N. But yeah, this is what this looks like. And there you go. This is the value of 15. Add 10 to 5, but only if true and 5 is less than 10. Otherwise, you pick one of them. This is 15. And here's add 15, which takes a function, takes a number and adds 15 to it. This is just to show the lambda syntax. The lambda is this nice Unicode lambda, like the actual Greek letter. I think it looks cool. So this is like in Haskell. This is we're saying that, well, this function has type natural to natural, and well, this value is something of type natural to natural. And what is this value? Well, it's a function that takes a natural number. You might have also have written this, like in Haskell. So, yeah, lambdas are a thing. And now let's get into propositions as types, because you need to understand this in order to do useful dependently typed programming. So we're going to import our syntax module. You'll see this open import, open in front of the import name here, which is just saying bring everything in this module to scope and treat it as like a top level variable here. You can hide stuff from modules import. So here we're importing some stuff. I try to keep it minimal. That's the kind of the stuff that we import from the standard library, but you can hide things. You can hide names. And now we're going to get into some of the actually dependently type stuff. So this type here is the equality type. And what this means is for any type set and for an X that is a member, for any type that is a member of set, and for any element of that type, give me an element of this type, and I'll give you back a set. Okay? And REFL, which is the sole inhabitant of this type, has type x equals x. So what this is saying is, for a value, so the only way that you're able to pattern match on this type, or that you're able to do anything at all with it, is if you have two values that are equal. Okay? So the x here is on both sides of this constructor. See that? So it's appearing both here and here. There is a difference between a type appearing on the left side of the colon and on the right side, but I'm not going to get into it exactly. What I'm trying to show is that even though this thing takes two parameters, you can only construct a value if really they were the same thing all along. So Agda is able to just compute this on the type level. So here we have a hole, which is the first result of running load, the command, the Control-C, Control-L command in this module. And this is the hole 0. And this hole has type 11 plus 4 equals 15, the value we defined before. That's the type of this. So this is how propositions as types is cashing out. The proposition that 11 plus 4 equals 15 is the type this. I didn't say it because I would just say the same thing again, but they are the same thing. Propositions are types. They just are. That's a fundamental fact in logic and computer science. And what is the inhabitant of this type? Well, it's the unique inhabitant of the type equality for these two values. And now I'm going to use a very powerful command, which is Control-C, Control-A, to automatically solve this. Agda is able to figure out that the proof of this proposition is the value of this type. That's the correspondence. Propositions are types, proofs are values or programs that show the type. A value of a type is evidence that the type is true or false. We're going to see some more stuff about this soon. If we wanted to prove that 11 plus 13 is equal to 15, that's just impossible. I hope that I don't have to convince you very hard of this. But if I and now I'm going to use the command to show me the context here. What I'm trying to show is that, and this is the output that we see, that I'm trying to show that the computer number 14 is equal to the computer number 15. You can't show that, really. We'll see more examples of using the context soon enough. So you could define other relations in terms of types, like a number being less than another number, or anything really. Well, any proposition. But there's another way to think about it. If a type is true, it's inhabited. It has at least one value in it. It's a set with at least one element. If it's not inhabited, it has none. And these two fundamental truth or falsity states are represented by these two types. This one is called bottom, and this one is called top. We good? Is it?
Yeah, it's fine.
That's a scary sound. It's a fire alarm. Okay.
Because it's late alarm.
Oh, okay. That's okay. Much less scary now. Right. So these two types are uninhabited and inhabited by a single thing, respectively. Bottom is also called false for obvious reasons. It represents the fundamentally false proposition. And top is called true. Top has the single inhabitant TT, and that value is evidence that the proposition represented by the type top is true. So we can now define relation based on these types with dependent functions. So look at this. This is a function that takes two natural numbers and returns a set. It returns a type. Okay? And let's think about the logic of this. If 0 is less than or equal to n, well, if we pattern match on the first argument, we know it's true. Like 0 is less than or equal to any other natural number. So we represent this by the type top. And I had this was supposed to be a whole, but we'll fill out the other ones. Now, what about this case? What if we have the successor of some number? If you don't know the piano, I guess I should have asked this, but the piano representation of natural numbers is 0 is a natural number, and the successor of a natural number is a natural number. That's an inductive definition. And that's what we're pattern matching on here. So the successor of a natural number, or the lowest a natural number can go, is 0. So this is at least 1, this thing on the left. And 1 is not 1, or anything above 1, is not less than or equal to 0. So this is the type bot. This is what we're trying to represent. This is the relation we're defining. And the type, and what about if you have two natural numbers that are both successors of something? Well, the left one is going to be less than or equal to the right-hand side if the predecessors of both is less than or equal to the right-hand side. So this is going to be that's a slow monitor. This is going to be this. We're just recursively calling our relation. And then we can have a little proof here that this thing works. Well, we should expect this to be true, right? 0 is less than or equal to 100. And we see what our goal is. What is the evidence that we have to provide that this is true? It's the type top, which has a single inhabitant. I wonder if we can ask Agda to just give us the type, the value of the type top. Well, of course it can. There's only one inhabitant. It knows from looking at the type that this thing is true, or it resolves it computes the type, and then it says, okay, this is what you have to provide. This is the evidence that you have to provide, and the evidence is trivial. We also have strict inequality. So here we want to say, well, 0 is not less than 0 this time. So we'll have bot there. This is also obviously false. I mean, something that follows anything else is obviously not less than 0. But 0 is less than or equal to any successor. So this is going to be top. And then recursion for the last case also. I have my cheats here. As you might know, live coding is tough. And in fact, because I am moving a little slower than I thought, I am going to blaze through the last of the latter part of this propositions as types module by just uncommenting the holes, and then we'll go through the code. Because I am being pressed for time here. We have quite a few things to get to. So what is this saying? A type-safe subtraction. We're saying that any m less than any n will provide an n, another natural number, only if you have a proof, or give me something of this type, that n is less than m. And here's what Agda is doing. If it sees 0 on the right-hand side, it already knows that the thing on the left is greater than or equal to it. So you can just provide the TT value. It pre-computed it. And so m minus 0 is obviously m. Now if you have m minus the successor of something, what should this be? I mean, you can't really ever give a proof that this is true. You can't ever give a proof of this part of the equation. And if you had a proof of this, you would have an inhabitant of the bottom type, which doesn't exist. So the way of expressing that is with this open and close parenthesis here. It's called the empty pattern. It's not unit like in Haskell or anything like that. And then if you have a successor of something minus a successor of something else, and a proof that the left-hand side is greater than the right-hand side, well, you just recursively call the subtraction function, removing on the predecessors of these numbers. So here we can test that our subtraction thing is correct, our subtraction function. And you guessed it, Agda is going to compute this automatically. It just knows by looking at the type that the two sides of the equation on it are the same. And that's basically the idea of propositions as types. I could do more advanced proofs, but I want to get to the programming with dependent types part of this. So we're going to go slightly faster here. This is a prototypical example of dependent types. It's a vector where you know the length of the vector at compile time. Doesn't actually mean you know it in advance. Obviously, you get user input and all that. But the point is that it's part of the type. Vectors in Haskell or in any language, well, most languages, usually the vector just contains some other type. They don't have a length associated to them in the type itself. Not so for this case. You have the empty vector. How's this type defined? You have the empty vector, which has length 0. And you have the cons vector, which has this constructor takes an element, takes another vector, and gives you back a vector with that many elements of that type plus 1. You're just going to stick the thing. You're going to stick the first element you received in front of it. And here is now I see that things are not, I can toggle word wrap, I think. Yeah. So that we don't miss anything. Here's the take function. I'm going to rely on the cheats. Whoops. Instead of filling this out. So the take function is, give me a number, give me a vector, I'll give you that many elements taken from the front of the vector. But in this case, you have to give me a proof that the number you're giving me is less than the length of the vector, right? Give me a number a, give me a proof that a is less than the length, and then I'll give you a vector, a long, from the first vector. And you might have seen this in Haskell. This is not, there's nothing fancy going on here. Taking 0 gives you back the empty vector. Taking successor of something, you take one element, you move to the back of the vector. Here's concatenation of two vectors. Let's just rely on the cheats. So if you have an empty vector, really you're concatenating an empty vector with the second one, so just return the second one. Whereas if you have something on the first vector, traverse it, put it in front of the result of concatenating the rest. Here's getting an element in a vector. Again, you have the length of the vector, and you have a proof that, maybe the word wrap was a bit of a bad idea, but you get the idea here. You have a proof that the index you're looking up in is less than the length. You'll get that out, you get something of that element back. Very similar to take an idea. Constructing a singleton, we're making good use of the singleton of the mix-fix operators here. Give me an element, I'll return a vector of length 1 with that element in it. Here's a little proof that our right index works. Auto-solve, baby. Agda just knows. You say that the type of this thing is looking up the index 2 in the vector v, which you've bound here. Yeah, there's let bindings in types, which is extremely awesome in my opinion. That is equal to 6. Yes, it is, of course. And some usual high order functions. I mean, map. Who doesn't love map? Just apply a function to a vector and traverse the rest of the vector, applying the function as you go. Here's point-wise application. So you have a function, you have a vector of length n that contains functions from a to b. And then you give a vector of a's, and you expect to get a vector of b's back. This is not a super usual higher-order function. It should remind you of applicative functors, but we are going to use it soon enough. That's why I'm including it here. We're also going to use replicate, which is give me an element, and I'll give you a vector of length n, whatever n is. N is being given as an implicit argument here. But when n is 0, again, same idea. When n is 0, return the empty vector. And when n is successor of something, put it on in front of a replication, like calling the same function on the tail. Here's transposition, which is if you have a vector of vectors, you should basically exchange the rows with the columns, which is using some clever application of pointwise here, which is why we needed it. Yeah, I won't have time to explain transpose, unfortunately. But it's cool. If you can stare at this code and verify why it works. Or you can just write a proof that it works. For any type A, and for any 1, 2, 3 elements of A, transposing this matrix should give you this matrix, right? 1, 1, 1, 2, 2, 2, 3, 3, 3, 1, 1, 1, 2, 2, 2, 3, 3, 3. Guess how we solve this? It's done. That's for any type and any 3 inhabitants of this type. Here's, I think this is our final higher order function, which is zipWith. You might know zip. If you don't know zipWith, it takes 2 vectors, a function that takes 2 arguments, and applies that function to the 2 vectors as it goes. That's why it's a zip. Zip is like a zips of a pen, so zzz, and then you get a single thing out of 2 strands. Let's look at a few more dependent types. Now, this is when it gets real. This is This is called the sigma type. That's that word. That's that letter here. Give me something of type A, and a function from an element of A to a set, and I'll give you back a set. So the fields of this are, the first field has type A, the second field has that function applied to the first field, to the element of the first field, whatever it is. And to show this dependent, the reason the sigma type is called the dependent product, and the reason is because it's a pair. It always has two values, projection 1 and projection 2, except that the type of the second pair, of the second element, depends on the type, on the value of the first one. And here's an example of this. So there's a function nat if false, list of top if true. Right? It just takes a bool, returns a set, pattern matches on the bool. If it's false, returns the type of natural numbers. If it's true, returns a vec for any natural number. It returns a vec of tops. And here is a value of a dependent product that uses this function. So this is a product of bools, and this function is the second parameter we give. So this function is, well, what should the type of the second value be? The first value is false, so it should be a natural number, which is why this compiles. The second example is, well, this is true. So the type of the second thing is this list of tops, 3 tops. I don't know why you would use that, but it's just to illustrate that you can have a product type that it varies depending on values. We can have expression and type signatures. Now I have to really go fast here, but this gets crazy. Like you can do a lot with it. Here's the type of set of natural numbers that are greater than 5. You just define it as a dependent product where the second element is a proof on the first value. And you can construct a proof that the value 7 is greater than 5. The proof of it is going to be TT, because it's computed in the type. But you can't produce a value of greater than 5 with the first element being 3. The type of this hole is going to be bottom. It's impossible to produce a value of bottom. You can parameterize this over the natural numbers, so you have greater than n. Here's the value 9 is greater than is of type greater than 7. Of course it is. All right, you with me? Still have quite a bit to get through. I'm going to have to blaze through this last part because I want you to see this cash out in a program, a simple program, but still. Let's get to this module, where we write a little matrix library. We're using the natural numbers. We're using our previously defined stuff. We're going to define a record here, which is num, takes a set, returns a set, has a bunch of fields, which are functions on this set. Some of them are values, but this is functional programming, so functions are just values. And what this is Agda's answer to type classes in Haskell. If you didn't know, when you're a type class in Haskell, just cache it. It just reduces to a dictionary at runtime. For this type, the implementation of this function is this. For that type, the implementation of this function is that. Agda just makes that a lot more explicit. This is some syntax to bring the members of this record into scope for the rest of the module. And here's how we declare instances. They are just values of this record. You define what you define all the fields of the record for this set, natural numbers, and for this set, the real numbers. This syntax for creating the record here is called copatterns, which I think is fun. It's basically you give the type of the record and you say what this function applied to this record is. The reason it's called copatterns is because Patterns, when you match on a pattern, you're deconstructing it to say, for this branch, do this. Whereas for a co-pattern, you're saying, from every possible angle, here's how you construct this. So you have to yeah, I hope it's a little hard to explain. But it's basically how to construct something based on the fields it has versus how to deconstruct something based on what it could be. It's a dual, co-pattern, category theory, haha, yeah. And this is how you say that this thing is an instance argument. It can be used as an instance argument. You say, you just put the keyword instance in front of it. So let's go over the matrix type and the functions on it. It's basically a new type over a vector of vectors. You have the number of rows and number of columns and any type for it. And you can add two matrices together as long as they have the same dimensions. This is what this function is defining. Again, mix-fix operators. So the way you sum two matrices is, well, you zip with the first vector, with the first layer of vectors, zip with the second one, sum whatever you find on the way. That's what this little nested zipWith is doing, applying it to the two matrices. I thought I toggled the word wrap. Yeah, here we go. So give me a matrix of A, another matrix of A. I'll give you another matrix of A with the same dimensions. Multiplying matrices is more interesting. Now you're saying, well, a matrix with dimensions R and C and a matrix of dimensions C and P can be multiplied to produce a matrix of R and P dimensions. Very natural to express. Won't really go over the implementation details here, but you can look at the recording again, stare at the code, make sure it works. Oh, I already told you to stare at this code actually, because it's using the transpose we defined on vectors. So you're going to have to stare at two layers of code actually. Here's a few other functions that are just nice to have. Give me a vector, and I'll construct a column matrix out of it, which is a matrix with a single column. So that has n rows, that being the length of the vector, and one column. And a vector to a row matrix has a single row and n columns. And this is just a synonym for transposing, but if you've seen matrices written in mathematical notation, they have this to the power of t thing, which is neat. Yeah, you've seen these infix declarations peppered throughout. That's just saying whether an operator associates to the left or the right. In this case, it's a single argument, so it doesn't really make sense. And the priority and how tightly it should associate. So that's a little matrix library. We can add, multiply, transform vectors into matrices. Simple stuff. And we want to get the pseudo inverse of a matrix now. That's a tricky operation. If you've ever tried inverting matrices before, you'll know that it's not a trivial algorithm. Like loop decomposition and verifying that a matrix is non-singular, that stuff is hard. So going back to the Lindy effect thing, Agda has a way of relying on that part of how much you can trust code, like whether you care about the code being correct. You can rely on code that has just been out there for a long time and kind of trust that it's correct by using the FFI. Agda is compiled down to Haskell. That's how it ultimately runs and creates stuff on the screen for us to use. And it has an FFI, so you can call Haskell code from Agda. You can also call Agda code from Haskell, which is interesting. And Well, there's not much to say about this one, except you might see this. You're going to look at this trust me being used, and this is exactly the point where it's like, yeah, forget about all the type safety stuff. Just trust me, this thing works. That's the actual name of the library, by the way. It's not. It's the actual name of the package. It's called trust me, and there's a proof in there that is anything is equal to anything else. Just trust me on this. It's correct. So this is how it works. Oh, gotta toggle word wrap again. There's, I think, 3 types of pragma for using the FFI. So this is telling the compiler, when you get down to compiling this part of the code, insert this Haskell code in there. Just import HS matrix. And what is that? Well, we'll see. Here's another pragma, the compile pragma. When you see this postulate, and a postulate in logic is something that we just state, this is true. Like let's pose this proposition. They kind of take, I guess they fight over the spot of things that are just true because they are with axioms. I think there are differences between postulates and axioms. I'm not actually sure, but that's how you just carve something out of thin air from Agda, and that's how you use that's what you tell the FFI. Whenever you see this postulate that takes a list of lists of real numbers and returns a list of real numbers, tell it to be invert matrix as list. This is Haskell code. This is the thing that it's going to cache out to. Instead of trying to compile this thing whenever you see it, just make it equal to this Haskell code. There's some conversion code here for turning lists into vectors and vectors into lists. I'm going to have to skip all of that, except for this part here, the trust me proof. Like, don't worry about it. Just, this is gonna work. Trust me. I just love the name. So we use from list of lists for calling the postulate. This is the inversion operator to the power of -1. First, you turn your matrix into list using our conversion function. Then you inverse it. You inverse it by calling the postulate, and then you convert the thing you got back with passing trust me's again to make sure that the dimensions match. So that's why you have give me a square matrix for any n. You have a matrix of dimensions n to n and n. I'll give you back n and n. So this is now an Agda function. Like this, it works on the Agda level. The proofs are going to be, or terms are going to be tested against the proofs that your n is, that your matrix is square and that the input is the same as the output, etc. And here's some code for displaying matrices. Again, we use the standard library for that. Yeah, it's just, there's not much to it. Just recurse over a vector and intersperse the thing with commas. Should look very similar to Haskell to you. And yeah, to show a matrix, you just use showvec. So the last module that we're going to look at is the main module. Yay, we're not just heating up the processor, we're actually running something. We do some imports here. Agda's relationship with I/O is, as you would expect, complicated. There's some syntactical, not just syntactical, there's some noise in this, like this level 0 thing, the fact that we have to run an I/O call, despite the fact that we're already running an I/O, like what's going on? Don't worry about it too much. It's really, you should sort of not look at this IO.run or the level, the level calls. This is just an I/O call to print a matrix. Give me a matrix, I'll give you an I/O operation that returns top. And here's our main function. let our matrix M be this matrix 2, 6, 3, 4. Let MInv be the inverse of it. And then we should see, well, what we should see here is, first we're going to print our matrix, then we're going to print its inverse, and then we're going to print the matrix times its inverse. And this should give us back the identity matrix. If I'm lucky, of course. So I have this little build command here. It's created by this Nix shell, where it's going to compile our code. It linked it, and we can just run this code, and there it is. Our matrix M is 2, 6, 3, 4. Its inverse is minus 0.4, etc. And it times its inverse is, whoops. Oh, Jesus. Was that right? Yeah, so 1, and then a 0.4 here, and then something to 10 to the power of minus 16, and then something to the power of minus 16, and then 1. So this is really minus some floating point error. This is 1, 0, 0, 1. That's the identity matrix. And yeah, this is, that's essentially the content. I'll just add a little appendix here, which is showing you what that Haskell module looks like. And here it is. Ooh, it's not actually using singletons. That's for a future talk. But this is using an external library. This Haskell file relies on an external library that is being fetched from Hackage. It's called hmatrix, and that implements the pseudo inverse algorithm. This is the Lindy part of our code. That code is out there. It's tested. It has been running for a long time. It relies on code that is even more well tested, like LAPACK and BLAS algorithms. And this little module here serves between our world of trusting the Lindy code that's just been out there for a long time, and trusting the theorem-laden, extremely type-safe world of Agda. And the ultimate point, I guess, the thing I wanted to leave you with here, is that the more convenient it is for expressing correctness, like a lot of the stuff that you saw in those types are pretty natural, like 15 is equal to 11 plus 4. You know, anyone can read that code and just understand it. The more convenient it is expressing the correctness of something, I think the more obsolete the trade-off between convenience and correctness is. Like, the less effort you have to spend translating your intention into something that is verifiably correct by a computer, the more you don't have to worry about, well, how many layers of tests and how much type foo do I have to do to make sure that this thing is correct. And I think Agda has a major role in this, because I think it's a quite beautiful language that makes it natural, and I'm using that word carefully here, to express what we actually mean when we write code. And I hope I've been able to convince you of that, or at least make it sound plausible to you. And that's it, an intro to Agda. Thanks again.
Thank you very much, Andrea.
Thanks, Magnus.
I didn't follow everything. Even though I tried, I've seen this twice now. Yeah. Do we have any questions? Anyone?
Yep, you have a question there.
We'll send them a mic.
Yeah.
Can you
show us what the type errors look like if you add an element to the matrix in the wrong place?
Yeah, I can do that. I just messed up my mic here. Yes, I can show you. You mean in the proof that of the transpose? Is that what you were talking about? Or if you just try to give... Yeah? What about it?
Yeah. What does the type error look like
If I just add, like, if I...
one element to one of the rows here?
Oh, if I... Oh, right, yeah. That's a good question.
I wanted to know what it looks like if you add an element here, yes.
Yes. So what do type errors look like? So here we added a matrix that is just not well formed. It has two columns in one of its rows, and then it has 3 columns in the other one. So if we try to load this module, it says, yeah, I guess it's a little bit hard to read unless you already know what you're looking for. But essentially, it's telling you the truth. Like, the successor of something is not equal to 0. It's trying to, when it's constructing this value, it's trying to match, when it gets to this point in the pattern matching of the first vector, it's going to try to make sure that both sides of its matching are 0. And one of them is going to be suck. And suck of anything is not 0. But yeah, if maybe a better type error would appear if you do this, because, whoops. So this is a matrix that is well formed, but it's not square. So now this is a much better error. Like 3 is not equal to 2. When checking that the expression matrix float is, if I had imported these things properly, it would look a little better. But 3 is not equal to 2 because you have 2 rows but 3 columns. So the matrix is not square. You can't invert it.
Thank you. Anyway,
No.
Any more questions? No, everyone understood everything.
Yeah.
Yeah.
You were the only one.
Yeah. Sorry.
Yeah. Oh, we have a question
Yeah.
there.
Shoot. You get a mic.
Yeah. Thank you very much for the presentation. It was very interesting to follow. The question is about, maybe sound a little weird, but the application of this type of programming. So as far, yeah, it's like like where practically there is a demand to use these techniques.
Yeah, that's a great question. And using Agda specifically, I know of at least one company that has hired for it, which is IOHK. When they've rebranded to IOG now. And they're doing blockchain stuff, and they're doing protocols between blockchains. So it really, really matters that the code they write is correct, and they use Agda to prove theorems there. But I know of programs developed using Agda, like a verified C compiler. Pretty sure it was developed using it, and that is used. I think it's called CompCert, and I hear it's used in like some serious applications, like aviation software and that kind of thing. It really can't go wrong, otherwise people die. Yeah, I'm not. Don't quote me on that second one, but I'm 90% sure that's an Agda thing. Yeah.
Okay. I have one question. How come you came in contact with Agda?
Yeah. The way I came in contact with it was I was into Haskell, and I was doing my master's degree in complex adaptive systems, which is this half physics, half computer science thing. But I would say it's a bit out there, but I think the fundamental question is, how are things the same? Like, what is the fundamental structure of these things? So I wanted to unite what I saw of that question in Haskell. Like Haskell is, type classes and uniform behavior across different types and everything. That's made me look for something more advanced in that space, and eventually that led me to dependent types and the master's was in Chalmers, which is where Agda is developed. So yeah, it was from Haskell to category theory to dependent types to joining that up with complex systems. And Agda was just a natural choice in Chalmers.
Okay, thank you.
Yeah.
Well, any more questions? No. Thank you very much, Andrea.
Yeah. Thank you.